Hello everybody. This lecture covers how the chain ladder method works in detail. It's a well-used method in the general insurance actuarial world, so I recommend you get comfortable with it. This lecture will cover the central equation, the key concept, and strengths and weaknesses of the chain ladder method, as well as going through an example calculation, so you can see how it works in detail. So let's start with the central equation. The central equation for the chain ladder method is y equals m times x. In this equation, y is the ultimate for each origin period we are modelling. X is the latest development point for each origin period, and m is the multiplier derived using the chain ladder method, and which will differ by each origin period. We can immediately see from this equation where the chain ladder method will have issues. That's where m is uncertain and or where x is uncertain. There are many tools in the actuary's toolkit, and so we should only use methods where it's appropriate to do so. This method is widely used, as there are many areas where it is suitable, but during this lecture I'll also flag up for you where it isn't. The key concept behind the chain ladder method is that there is a true but unknown development pattern for the segment we are modelling, and we're going to analyse our historical data to estimate that pattern. We'll then project that pattern forward to derive the future development of claims all the way up to the ultimate position where the policy life cycle is complete for this segment. We can see from the key concept just how important it is to model homogeneous data, as otherwise our historical patterns will not be representative or appropriate to use for the future. This is why we spoke a lot about segmentation in lecture 2, and if you haven't watched that lecture I recommend you go back and understand exactly all the different things you need to do to prepare for using this method. So the way the method calculates this true underlying development pattern is by looking at link ratios. Link ratio is the ratio of successive development period data points for a given origin period. Let's illustrate this through some actual data and calculations. What we're going to do is we're going to take a cut of data from our individual claim database covering incurred claims for a long tail class, say private motor, third party bodily injury. I'm going to use annual origin periods, accident years, just to make the example simple, and I'm also going to use annual development years. It's likely this level of granularity will be too high for most of your modelling purposes, and you may well choose to use more granular origin and development periods instead. Similarly, we wouldn't just look at incurred data when modelling a segment, but it's fine to use that simplification for our example. So, the first thing we do is put our data into a triangle shape, with data in the top row relating to 2011 accidents, through down to the bottom row, which will relate to claims from the 2020 accidents. Let's go ahead and fill in data for the 2011 accident year. We can see that after one development year, i.e. at the end of the 2011 calendar year, we have 50 units of claims incurred. Then after 2 development years, i.e. the end of the 2012 calendar year, we have 100 units of claims incurred, and we go all the way up to the end of the 2020 calendar year, i.e. the 10th development year, where we have 176 units of claims incurred. Obviously, getting all this data in this format requires a lot of calculations, so we'll be using a database tool to get our data into the right shape. And we can then roll this out across the whole triangle as follows. So here we have the first column showing data in the first development year for all the different accident years, and that's all we're going to have for the 2020 accident period because there is no future development in our data set going up to the end of 2020, and then subsequent columns have the next development data and so on and so on. As we have more development data for the older origin periods, we must naturally end up with this triangle shape of data for our model. Let's now zoom in on the first and second columns of data. We can calculate the first column of link ratios by simply dividing the second column by the first, as follows. So when we look at the 2011 accident year, we get a first link ratio of 2, which is simply 100 units divided by 50. So 100 over 50 is 2. If we look at the 2011 accident year, we get a first link ratio of 1.5, and that's 150 units of claims incurred after 2 years divided by 100 units of claims incurred after the first year. So 150 divided by 100, 1.5. This is a fundamental calculation in this method, so make sure you're comfortable with what you're seeing here. The red figures are the calculated link ratios, whilst the green figures are the actual development data from our individual claims database. If we bring back the whole triangle of data, we can then roll out the link ratio calculations for the whole triangle to get a link ratio triangle, like so. At this point, often actuaries will hide the actual development data and focus only on the link ratios. However, for this example, I'm going to keep it on show. And I will also caution against ignoring the actual data points. We need to know if individual origin or development periods are particularly big or small when considering how valid they are. So don't jettison this valuable information too soon from your modelling thought processes. Our job now is to analyse this historical data to find the true underlying development pattern which we will apply to all future development in this segment. In this example, it's motor third-party bodily injury claims. I'll talk a lot more about how I personally go about doing this in the next lecture. For now, it's worth noting that for each development period, we could take some average of the historical link ratio values in that development period. For example, using a simple or weighted average of them, with or without a decay factor, considering all or part of our historical data. We could use some benchmark, internal or external, or we could use expert judgment to just pick a figure. We may decide that some individual link ratios, or groups of them, for instance an individual year or a development period, are just not representative of future development and choose to exclude them from our calculations. Again, I would note caution on this point. Data is almost always a scarce commodity for reserving actuaries, and so only data points which are really not representative and which unduly distort our model should be removed. It may be that better segmentation would remove these issues and retain all of our valuable data. Having said that, sometimes data errors are represented by one very high link ratio followed by a very low one, and it may make sense to remove such distorting link ratios from your model entirely. So, having selected our link ratios for each development period, we derive a set of selected link ratios. These are shown in the row down at the bottom of the screen in blue. So you can see that in the first development period, I had a range of link ratios from around about 1.5 up to 3, and the selected I've gone for is 2, so somewhere in the middle of these link ratios, and we've done a similar process for all of the different development periods. You'll note here we have a value of 1 highlighted in yellow. This is the tail factor, and it is there to cover the situation where we require a ratio to deal with future development beyond the end of our data triangle. I'll talk more about that later in the lecture. For now, just note that it's based on no specific historical data, as our data triangle doesn't go that far. We can also add a couple of additional rows at the bottom. These are firstly the cumulative link ratios, which are simply the product of the incremental link ratios from that development period on. So we get 3.26 as the cumulative link ratio from development year 1 onwards. So that's 2.01 times 1.23 times 1.17, etc., etc. And this row of data is actually the value of m we need for our central equation. We also show the development percentage, which is simply the latest development data divided by the ultimate position for each development point. It's simply 1 divided by m. So 1 divided by 3.26 gives us 31%. This value is a useful test of where our data is sufficiently developed to fully rely on the chain ladder method. The lower the development percentage, then the greater m must be, and thus the reliability of m and x can fall. You can get classes where development is long but yet stable, although generally long-tail classes are more volatile due to more complex claims and more disputes, or simply just claims not having progressed far through the policy life cycle of that stage of development. Having selected these link ratios, we can then apply them back upwards to fill in the bottom right of our exhibit to form a square or a rectangle. So here we can see that a link ratio of 2.01 will be used to move the 2020 accident year from the first to the second development year. Similarly, a link ratio of 1.23 will be used to move both the 2020 and 2019 accident years from the second to the third development year. We can now use those link ratios to complete the expected development data in the bottom right of our triangle. So, the 2020 accident year moves from 50 incurred at the end of the first development period to an expected 101 units incurred at the end of the second development period, and so on and so on. Note how the first link ratio only impacts the newest origin period. And we can keep following these link ratios to the right for each accident year, completing the development to the end of the triangle, the 10th development year, and then using the tail factor to take us to the ultimate position where the policy life cycle is complete. If we want to test our y equals m times x equation, we can look at 2020 here. So we have an x of 50, the latest development data. We have an m of 3.26. We multiply those together and we get our y of 163. We can start to draw some conclusions here about where the method will be strong and weak, considering the same y equals m times x equation. The newer origin periods will have the most link ratios applied to them, and so we'll be least certain about the value of m in our equation for those origin periods. Furthermore, many of the claims which will ultimately be paid on the newer origin periods will have made little progress through the policy life cycle, and so we'll be least confident about the value of x in our equation too for those newer origin periods. So we can conclude that we'll be least confident in the results from this method in the newer origin periods. It may even be that we have insufficient confidence and don't feel able to use this method for newer origin periods. In this case, we would need to use another method or consider changing our segmentation. As a rule of thumb, where m is greater than 2, then we should be considering if the chain ladder method is suitable. Although, as mentioned earlier, you can get classes with long but stable development, and vice versa. This is another reason why splitting segments into large and small cohorts can be helpful, as we can trust the chain ladder method when applied to our small claims dataset, which will be much shorter tailed, but may need to use something else for the large. We can also use the small ultimate as a guide for setting our more difficult large ultimate for a given origin period. We can also note two things about the link ratios for the later development periods. Firstly, we don't have much actual data from which to derive the true underlying development pattern for these later periods. For example, for the 10th development period, we only have one data point, so it's unlikely that this estimate of 1.01 will be a reliable estimate of the true underlying development pattern. There are a few mitigating factors here. If our triangle of data is long enough, then the policy life cycle may be complete by the later development periods, and so the link ratios for them may be 1, in which case we can rely on them more. This is yet another reason why we need to segment optimally to maximise the number of segments and hence amount of business where we can be certain of capturing all the development to ultimate in our models. Also, when selecting the link ratios which represent the true underlying development pattern for later periods, we don't need to treat each development period in isolation. Instead, we can consider trends over a number of periods to get greater confidence or to take action where we're not confident. So, for this example here, we could fit a curve to our incremental link ratios, or we could flatten development, setting all these link ratios to 1, or we could use a benchmark development pattern. Going back to the second point, which is immediately apparent for later development periods, we can see that the expected link ratios for later development periods impact many more origin periods and hence are relatively more important to set correctly. Again, this can be mitigated by development being finished or close to it in these later periods, represented by link ratios close to 1. If later link ratios are still large, then we should be taking mitigating action. Getting more development data will be a good start, seeking benchmarks and reassessing our segmentation too. In this example, we can see that our earlier selected link ratios are relatively high, 2, 1.23, 1.117, and then these trend down close to 1 by the end of the triangle. This is the normal pattern we would expect, as over time more and more claims have completed the policy life cycle and hence aren't developing anymore. There are exceptions to this general pattern. For example, limitation periods can distort when claims are made upon insurers, but we should at least be suspicious when we don't see things trending down towards 1 like this. We noted earlier the tail factor required to take us from the end of the triangle to ultimate. We can use similar techniques to estimate this value as we did for the later development periods, fitting curves, seeking benchmarks and optimizing segmentation. I'll talk through this a little more in the next lecture. So hopefully you are now much more clear on how the chain ladder method actually works. It's a very powerful technique to use where you have stable, short tail policy cohorts that have not been distorted by internal or external factors. It's simple to calibrate and explain to stakeholders. However, as noted, it can and will struggle with long tail classes, where there are distortions to historical or future development and where the history of claim development available to the actuary is not sufficient. In the next lecture, I'm going to talk you through how I would apply this method in practice to an example dataset. Reserving is an art, not a science, so it's not a step-by-step set of instructions, but it should be helpful in explaining how I go about ensuring my historical data is reliable and that my predicted ultimates are as reliable as possible from the method. You should be able to see the next video in this series on the left-hand side here, so please click to move on to it now. As usual, please also like and subscribe to support these videos. Again, you should be able to see a small circle which you can click to subscribe. And do let me know your comments and feedback on these videos in the comments section below. Thank you.